Okay, geometry. Welcome to lesson 3.5 notes covering symmetry. So symmetry, I think, is a topic that you know about, right? So we'll be talking about symmetry amongst figures. Again, it's about a mapping onto oneself kind of thing. So our faces are symmetrical because the left side of our face looks similar to the right side of our face. So we could reflect down the bridge of our nose, and typically your eye would line up with your eye. So symmetry, that kind of stuff. Okay. So let's take a look here. All right, so it says identify transformations for symmetry. What transformations can be used to map the figure onto itself? Why can some figures be mapped onto themselves? Okay, so it says a figure has symmetry if a rigid motion can map the figure onto itself, right? This idea of being on to itself. So there are two types of symmetry. The first one is called reflectional symmetry. So reflectional symmetry is where there's a line of reflection, right? And you could reflect the figure over that line and it reflects onto itself, okay? That line is called the line of symmetry, right? So when you're doing these, you're looking for your lines of symmetry. Now this is kind of like a star pattern, I suppose. So notice that it's wider than it is taller. So there's going to be two lines of symmetry. The first one I'll do is vertical, going right down the middle. This would be the first line of symmetry, or the reflectional symmetry. So if you took this left side and reflected across, and the right side, they would map onto themselves, right? So this is line L. So there is one type of transformation. The second one would be this horizontal line going through, call this M. And again, if you brought the top down and the bottom up, they'd line up on themselves. So that's line M. So you also have reflection across line M. So there's your reflectional symmetries. If this looked more like a square, again, I said it's wider than it is taller, then maybe you could go diagonally. So some figures have these diagonal lines of symmetry, but this one does not. Okay. And then lastly, you have rotational symmetry. Rotational symmetry is this idea that if you rotate the figure less than 360, so again, notice it's less than 360, because if you go 360, of course, you're back onto yourself. Okay. So here, if we let the center be point C, typically they're multiples of 90, right? So if we were to take this figure and go 180 degrees, so let me use blue. So if we took this figure and went 90 degrees counterclockwise, this point would end up here. Okay, again, because it's wider than it is taller, so then if you rotate it 90 degrees, now it'd be taller than it was wider, so it would not line up. That point would go there, and this point would go here. They'd be up high, and that'd be the figure's top part, this part. But if you rotate it 180 degrees, this part will go here, and this part will go up here, and this will be lined up on itself. So if you take this and go 180 degrees this way, you will map onto yourself. So it does have rotational symmetry if you go 180 degrees up at the center of this figure. And there you go. There are the transformations that will map this figure onto itself. These are the reflections the symmetries we're talking about. Okay, so it says how many lines of symmetry does a regular hexagon have? The word regular essentially just means perfect. It's a perfect hexagon. So all of these angles are congruent, and all of these sides are congruent, right? That's what regular means. So when we're talking about lines of symmetry here, this figure is going to have every line of symmetry in the world possible. So here, okay, you can go from opposite vertex to opposite vertex. So this would be a line of symmetry. That's one. This would be a line of symmetry. Again, splitting the figure in half, that's two. This would be a line of symmetry, that's three. So there's 1, 2, 3. You can also go down the midpoints of the sides. So if this is a midpoint and this is a midpoint, go straight down. There's a line of symmetry. 4, again, splits the left and right side. Again, midpoint, midpoint. There's a line of symmetry. There's 5. And again, midpoint, midpoint. There's a line of symmetry. There's 6. And that would be all of them. So there are 6 lines of symmetry. Notice that a hexagon, lines of symmetry. My M's, my E's just blurred together, sorry. Notice that the hexagon has 6 sides, the regular hexagon, so it has 6 lines of symmetry. Okay, next one. All right, let's talk about rotational symmetry. For what angles of rotation does this figure map onto itself? Well, this is an equilateral triangle. So again, an equilateral triangle is a regular triangle. So again, all the angles are congruent, all the sides are congruent. So this is going to have perfect rotational symmetry. So because it is a regular figure, what we're going to do is we're going to use the center here, and we're going to take 360 and divide it by the number of vertices or number of sides it has, 3. And that's going to be 120. So this figure is going to have 120 degree rotational symmetry. So if I go counterclockwise from A, 120, that A is going to land on C. A would be on C, C would be on B, B would be on A. If I take A and go 240, that'd go through C and around to B. So it also has 240 degree rotational symmetry. And if I take A and rotate it, 3 120s, which would be 360, we get back to A. But remember, we don't count 360 degrees, but we stop there. So this figure is going to have 120 degree rotational symmetry and 240 degree rotational symmetry about its center. Okay. Now, so it has 120 and 240. Now I'm going to click and go to Savas so we can take a look at this visually, right? Again, gotta love technology, how it makes things a little bit more eye-opening. So I have this slider here where I can actually rotate it. So let's see what it does. So see how it's rotating? So not 90, but if I go, there we go, 120. See how it maps on itself? So A prime's down here. And then if I go to 240, there we go. A is down here now, maps on itself. And then 360 it finishes, right? Back to where it began. So that's why it has 120 and 240 symmetry. So you take that 360, which is the total rotational, to get back to the beginning, and divide by the number of angles or sides, whatever you want to do. That's if it's regular. Okay, next one. Last one, last one on this video. So now what about a parallelogram, okay? Well, a parallelogram is not regular. So let's make that known right now. This is not regular. So it's not going to have perfect rotational symmetry, okay? So here what we're going to do is we're going to say, okay, I think that, again, it's wider than it is taller. If I take A and rotate it 90, A is going to come down here somewhere, and it's going to get tall, which would not line up. But if I take A and rotate it 180, I think I'll get over here to C. I think A would go to C, I think C would go to A, I think D would go to B, and B would go to D. So I think this has 180, and I also think it has 360, right? But that's it. 360 doesn't count. So it only is going to have 180 degree rotational symmetry. 180 degree rotational symmetry. So when your figures aren't, I don't know, like they're more rectangular shape, right? They're longer than they are taller. You're not going to have all the rotational symmetries in the world. Like if this was a square, I would take 360 and divide it by 4, and that would give me 90. This would have 90, 180, 270 rotational symmetry. But because it's not a square, because it's not regular, it only has some rotational symmetry. All right, so let's take a look here at Savas again. This will, again, visualize what we're looking at. So let's go to example 2, the parallelogram. So now watch when I go. So when you're thinking of 4 quarters, right, 90 degrees. So if you go 90 degrees, notice, right, as I said, if I can get there. There we go. Now you're taller than you are wider, right? So that's 90 degrees. But if you go the next 90 to 180, you can see you line up, right? 270, again, you'd be taller than you are wider. So you're not symmetrical there. And then if you go 360, you're back to the beginning. So the only rotational symmetry it has is 180. All right, so that's the end of the first video. Stay tuned for the second video.